Welcome back. In today's presentation, I would be dealing with the differential form of the momentum equation and its boundary conditions, and then cover some simplifying assumptions. We have so far obtained the momentum equation for a finite control volume. That is a very useful theorem, but it cannot give us the velocity field at every point of the flow. We now obtain the differential form of the momentum equation by applying the momentum theorem to an infinitesimal control volume, as was done for the continuity equation. The equation of motion so obtained is applicable to every point in the fluid field, enabling us to obtain the entire velocity field. This is not possible with the integral approach followed so far. This equation of motion is a vector equation, and we can write three scalar equations, one for each of the coordinate directions. Let us consider the scalar component equation in the x direction. Imagine a control volume with the dimension dx and dy and unit depth in a two-dimensional flow. Let the velocity component in the x direction Vx be represented by u and the velocity component in the y direction be represented by v. Now the momentum theorem states that the material rate of change of x momentum contained within the control volume is equal to the net x force applied on the control volume. The Reynolds transport theorem is used to obtain the material rate of change of momentum in terms of the rate of accumulation of momentum plus the net efflux of momentum. Now the x momentum contained within the control volume is delta x delta y, the volume, times rho, the mass contained within the control volumes, times the horizontal velocity, the x component of velocity u. So rho delta x delta y into u is the x momentum contained within the control volume. The rate of accumulation is obtained by taking the partial derivative with respect to t, and this gives you rho delta x delta y into del u by del t, assuming an incompressible flow. To obtain the x momentum efflux, consider the four segments of the control surface. Segment 1 with its outwards normal in the minus x direction. The mass flux across this is minus rho u delta y. We have used a minus sign because this is an influx. We use positive sign for efflux and negative sign for influx. So the x momentum crossing this surface per unit time, that is the x momentum efflux, is minus rho u delta y into u, or minus rho u square delta y. The efflux across surface 2, which is delta x distance away from surface 1 horizontally, is positive and is obtained by using the Taylor series expansion of rho u square delta y as rho u square delta y plus del by del x of rho u square delta y into delta x. The mass flux across surface marked 3, which has an outward normal in the minus y direction, is minus rho v delta x. Negative because it's an influx. And the x momentum flux across this surface is this mass flux times the horizontal velocity u. So it's minus rho vu delta y. and then across surface 4, delta y distance away in the y direction is again obtained by the Taylor series as rho vu dx plus del by del y of rho vu delta x delta y. Putting it all together, the net efflux is then simply rho times del u square by del x plus del vu by delta y into delta x delta y. This is net efflux that we calculated, and we expand the term delta u square delta x and delta vu by delta y to obtain the net efflux as rho into 2u del u by del x plus u del v by del y plus v del u by del y into delta x delta y. Now, if we use the continuity equation that we obtained earlier, delta u by delta x plus delta v by delta y is 0. So, multiplying this by u, the one of the first term and the second term cancel out, and so we get the net efflux as rho into u delta u by delta x plus v into delta u by delta y into delta x delta y. So, the material rate of change of x momentum associated with the control volume, that is equal to the rate of accumulation plus the net efflux, becomes rho times del u by del t plus u del u by del x plus v del u by del y into delta x delta y within the red box. This we carry forward. Now we have to find out the forces acting on this control volume. The forces are of two kinds: body forces and the surface forces. The body forces are given on per unit mass basis, and so the mass of the control volume being rho del x into del y, and if Fx is the component of body force in the horizontal direction per unit mass, then the total body force is simply rho Fx del x into del y. Now let us discuss the surface forces due to stresses. The normal surface forces in stationary or non-accelerating fluids are nothing but pressure forces. However, when the fluid elements are stretching, there are additional stresses due to viscosity. The normal stresses are then given by what are termed as Newton-Stokes relation. The normal stress in the x direction is given as sigma x is equal to minus p plus twice mu del u by del x. Minus p, the pressure here is the hydrodynamic pressure, and twice mu del u by del x is the normal stress, the normal viscous stress because of stretching of the fluid element in the x direction. And if we analyze this, the normal forces in the x direction can be written like this. On surface 1, with normal in the positive x direction, the left face of the element, the normal forces would be the normal stress P minus twice mu del u by del x multiplied by the area, which is del y into 1, the unit depth. Similarly, on the surface 2, on the right side, the force is now obtained by a Taylor's expansion of the force in 1. This force is towards the left, the force on one is towards the right. So the net force is del by del x of minus p plus twice mu del u by del x into del x into del y. Similarly, the shear forces on surface 3, the bottom surface, the shear forces to the left, the shear stress tau xy by Newton's law is mu del v by del x plus del u by del y multiplied by the area del x into 1 and minus sign because it is towards the left. Similarly, on surface 4, the top surface, by Taylor's expansion, we get this quantity. This is towards the right, so it is positive. The net of the two is this. Putting them all together, the net rate of change of momentum, which is the accumulation plus the efflux term, is equal to the net force. And if we use the continuity equation for the incompressible flow to simplify the right hand side further, this can be written simply as rho times del u by del t plus u del u by del x plus v del u by del y. This is equal to rho fx, the body force terms, minus delta p by delta x, which is the pressure force term, plus mu times delta square u by delta x square plus delta square u by delta y square. This is the viscous force terms, the net viscous force terms for all the surfaces combined. We can similarly obtain the equation in the y direction, and the only difference would be that u would be replaced by v and fx, the body force in the x direction, would be replaced by fy, delta p by delta x by delta p by delta y. We could combine these equations into a vector equation, and the vector equation would be rho into dv by dt plus v dot del v, where del operator is I times del by del x plus j times del by del y plus k times del by del z is equal to rho f minus delta p plus mu del square, the Laplacian of v. This famous vector equation is known as the Navier-Stokes equation, and this is a fundamental equation of fluid dynamics. For inviscid flow, the viscosity term disappears, and we get, after dropping the last term because of viscous forces, we get rho times del v by del t plus v dot del of v is equal to rho f plus delta p. This is called Euler equation and is applicable only when the flow can be considered as non-viscous. This equation, if we consider this in 3 dimensions, has 4 unknowns: the velocity component Vx, Vy and Vz, and the pressure P. But this system of vector equation consists of only 3 scalar equations. So we need a 4th equation. And the continuity equation del dot V constitutes the 4th equation to complete the system of equations for incompressible flow, assuming that rho is constant throughout the flow. Let us now discuss the boundary conditions applicable to this equation in viscous flows. Clearly, there should be no relative velocity normal to the boundary at the solid boundaries of the flow field, for otherwise the fluid will penetrate the boundary. Thus, V dot n should be 0. No fluid should flow out of a boundary or flow into the boundary at stationary, impervious, solid boundaries. Extensive experiments have established that for real fluids under continuum approximation, the relative tangential velocity at a solid boundary is also 0. This is called the no-slip boundary condition. The fluid may be moving relative to a solid boundary, but at the boundary, the velocity of the boundary would be same as the velocity of the fluid. Or rather, the velocity of the fluid would be same as the velocity of the boundary. If the boundary was stationary, the fluid at the boundary would be stationary too. There are two exceptions to this, two known exceptions. One is that helium at 4 degrees absolute behaves strangely and it may slip at the boundary. The other exception is for rarefied flows. When the density of the fluid is so low that the body dimensions are of the same order as the mean free path, then the no-slip condition cannot be applied. There would be slip at the boundary. Another way of expressing the no-slip condition is to say that for real fluids, there is no jump or step change in the velocity at a solid boundary. That is, the velocity field is continuous with that of the solid. At the interface between two fluids, including a free surface between a liquid and a gas, the shear stresses too do not experience a jump in their value. So whatever is the shear stress value at the interface in one fluid, the same shear stress is there in the other fluid at the interface, as shown in the figure here. The pressure also is continuous across a fluid-fluid interface, except for cases where the surface tension effects are appreciable. So, the continuity of pressure can be assumed only if the surface tension effects are absent. In most of the flow, in the rest of this course, we'll assume the surface tension to be negligible so that the pressure can be taken as continuous. At a liquid-gas interface, because the density rho and the viscosity mu of gases are much smaller than the corresponding quantities for liquids, the free surface of the liquid can be approximated as a constant pressure surface. Because of continuity of pressure, the pressure within the liquid at the interface is equal to the pressure of the gas at that interface. And since the densities of the gas is very low, the pressure variation within the gas are negligible, and therefore everywhere the pressure can be taken as the same. In this picture of a wave in ocean, the pressure in the air can be taken as atmospheric, the same value over the distance of the wave height. And so the pressure within the liquid at all points at the interface at the surface of the wave would be equal to P atmosphere. When the velocities are comparable on the gas and liquid sides, the fact that the shear stresses on the two sides of the interface are equal and that the viscosity of gases is much smaller than of the liquid requires that the shear stress at the interface be smaller than elsewhere within the liquid. On the liquid side, therefore, the velocity gradient near the interface will be much smaller than elsewhere. In the gas side, even with a large velocity gradient, because the viscosity is very small of the gas, the shear stress will be low. So this velocity gradient is going to be very small. In fact, as one approximation, we can neglect this velocity gradient and we can assume that the velocity gradient here is zero. If we were interested in studying the liquid side motion, we could neglect the velocity gradient on the interface and set del u by del y is equal to 0 at the interface on the liquid side as stated earlier. If we were interested in studying the motion of the gas, we would compare the shear stress at the interface with that elsewhere within the gas, and this would not be negligible. So while considering the liquid phase, studying the liquid phase, we can assume the shear stresses to be 0 at the interface. But if we were interested in studying the motion of the gas near the interface, the shear stresses at the interface within the gas cannot be neglected. In fact, they would be the highest, and the velocity gradient would be maximum there. Now let's consider the air-driven motion like the ocean waves with the velocity profile would be as shown on the left. Is the air velocity which is driving the waves in the liquid. Of course, there would be continuity of velocity at the interface. The shear stresses would be maximum at the interface. In fact, it is these shear stresses which are driving the motion in the liquid. And these stresses would slow down the gases, the air, the atmosphere above the ocean. We summarize the boundary conditions in a viscous flow by this table. At an impervious solid fluid boundary, there is no relative tangential velocity, zero slip. There is no relative normal velocity, impervious solid. There are no conditions on pressure and shear stress. At a fluid boundary, the relative tangential velocity is again zero, no slip. Relative normal velocity is again zero. We are again assuming there is no penetration of one fluid into another fluid. The pressure is same on either side for negligible surface tension. The shear stress is same on either side. Pressures and shear stresses and velocities are all continuous. The approximate conditions for the liquid gas interface, for the liquid side only, the relative tangential velocity is zero, the relative normal velocity is zero again, the pressure is the same, equal to the gas pressure and gas pressure can be assumed constant, and the shear stresses are negligible if the gas side velocities are not very large. With these boundary conditions, we are now ready to solve problems. But before that, we state some important simplifications that help us solve this equation. This system of 4 equations, the vector equations for momentum plus the continuity equation, is a formidable system. Second order nonlinear equations, all coupled. It's not easy to solve. So we look for simplifications wherever possible. First simplification is simply steady flow. The first term in the Navier-Stokes equation drops out, and we get the system where one less independent variable. Then simplification because of dimensionality of flows. If only one independent space variable, for example, we have flow through a channel, and we can assume the flow to be uniform, that at each section of the channel the velocity is uniform. That is, it does not vary across the cross section of the channel. Like so, we can write Vs, the velocity in the S direction, the downstream direction, is a function only of S. If it is a uniform channel, then Vs is constant. But if the cross section of this channel varies slightly, so that is a very slowly varying channel cross section, then Vs is a function of S. It can vary, and by simple application of continuity equation, V times area at any section is the same as at any other section. Such a flow is not truly one-dimensional because there has to be a component in vertical direction of the flow here. But if the channel is varying slowly, we can consider the crosswise component of velocity to be negligible and the variations in the crosswise direction to be negligible, and the flow can be considered quasi one-dimensional. This had been discussed earlier. Flow between two parallel plates. The distance between the plates is constant, and so there is only one component of velocity, Vz, and which is a function only of y, the distance in the vertical direction. It is not a function of x. In an axisymmetric flow in a pipe, there is only one component of velocity, Vz, and this is a function only of r, the radius, that is the distance from the central axis. It does not depend upon the angle, it does not depend upon z. So there is only one component of velocity, Vz, and which is a function only of one independent space variable, r. We introduced two-dimensional flow earlier, where the flow varies within a plane but is the same in the third direction. So there are only two independent space variables, x and y, and in the z direction there is no component of velocity and there is no variation with the z direction. Then the equations governing the flow are as listed here. Only two components, u and v, pressure P, only two space coordinates x and y, and of course the time variable. Then there is a concept of fully developed flow. We've seen earlier that as a flow enters a pipe, the velocity profile changes down the pipe, but only up to a distance which is termed as the entrance length. Beyond this entrance length, the flow can be taken as fully developed. So this velocity profile is the same as this velocity profile. There is only one component of velocity, Vz, and it is a function only of r. It is not a function of z. Since the velocity does not change down the pipe, clearly there is no acceleration. And the equation of motion simply reduces to this. The left side drops out. We have assumed that the weight, the body force does not play a part, so the pressure forces balance the viscous forces. We'll solve this equation shortly. So let's summarize these simplifications. The full development means dropping off the inertial term in the Navier-Stokes equation, rendering the equation linear, because it's only the acceleration, the inertial term, that contained the nonlinear portion v dot del v. So if there is no inertial term, there is no nonlinear term that renders the equation linear. There's a big advantage. Linear equations are a lot easier to solve than non-linear equations. There is no change in velocity in the flow direction, leading to dropping of the streamwise independent variables. So del by del x, all terms of del by del x are dropped. Of course, we retain del p by del x, and we will elaborate on this a little later. Another simplification is because of symmetry, which leads to reduction in number of independent variables. In two-dimensional flows, there is a reduction in number of dependent variables. Now, one less dependent variables, and there is a reduction in number of independent variables. There is one less independent variable as well. Let us now apply these equations to solve an example. We consider a channel made of two parallel plates with a pressure gradient applied along the axis. This flow is known as the Poiseuille-Couette flow. The plates are infinite in length. To be distance apart. We take the origin in the middle of this channel so that the upper plate is at y is equal to plus p and the lower plate is at y is equal to minus p. Let us assume that the lower plate is stationary while the upper plate is moving with a constant velocity v naught. We are interested in steady flow, so this plate has been moving for a long time, infinitely long plate. We assume the flow to be steady, incompressible, fully developed, no changes in the x direction. There's an interesting argument about this. Since this channel is infinitely long, so there is no natural origin within this channel, no natural origin in the horizontal direction. If I close my eyes for 1 second and somebody moves the channel in the time being, and I reopen my eyes, I will not be able to tell that the channel is moved. This implies that the flow pattern that we see within the channel should not depend upon the location of the origin. It should be same everywhere. It cannot be a function of x. If the flow is one-dimensional, there is only one component of velocity, and that is in the x direction. Vx, and we label it u, and this is a function of only one space variable, y. So u, a function of y, is the only component of velocity. Now let's consider a small element or a control volume within this of length dx and height dy. Let's take this out. There is a pressure force P dy acting on this face. By Taylor's expansion, the force on this face is P plus delta P by delta x into dx into dy. There is shear stress tau dx on this side. There is a shear stress by Taylor's expansion tau plus del tau by del y into dy into dx on this side. These are all the external forces applied on this. And so the force balance gives you minus del p by del x plus del tau by del y is equal to 0. Since there is no acceleration, all the forces must sum out to 0. Now for tau, the shear stress, we plug in mu del u by del y by Newton's law of viscosity, and so the expression is now this. If I consider the motion in y direction or the equation in y direction, obviously there is no acceleration in the y direction, there is no motion in the y direction. The forces in the y direction are P dx on the lower face, P plus del P by del y dy into dx on the upper face, and the weight of the element g times rho dx dy. And sum of these forces should be 0, and that gives you minus del P by del y is equal to rho g. Simple integration of this would give you P is equal to minus rho gy plus some function of x, because it's only the partial derivative with respect to y is rho g. So when we integrate, a function of x or a constant can be added. Now, let's go back to this equation. If I take the x derivative of this will drop, the first term will drop. So del p by del x would be function of x alone. Del p by del x would be a function of x alone. Now look in this equation. This is a function of x alone, and this is a function of y alone, because u is a function only of y. So one term is a function of x alone and the other term is a function of y alone. Then each of these terms must not be a function of x or y, but should be a constant. And so we can equate the two. Del p by del x is replaced by p prime, and we get del square u by del y square is equal to p prime by mu, and which is a constant. P prime by mu is a constant. That means p prime is a constant. Delta p by delta x is constant. Or pressure gradient in the streamwise direction is constant. The pressure is varying linearly. This equation, which governs the flow through this channel, can be integrated rather easily. There is another approach that we can take using the Navier-Stokes equation that we obtained earlier. When we have two-dimension x and y, as in this case, is a two-dimensional plates, there are a lot of terms that disappear. This term disappears because u is not a function of x. This term disappears because the flow is steady. This term disappears because u is not a function of x. This term disappears because v is 0. There is no vertical component of velocity. This term disappears because there is no body force in the x direction. There is body force only in the y direction. This force disappears because u does not vary in the y direction. This term disappears because of the steady flow, or rather there is no v component of velocities. These terms also because there is no component of velocity. Because this del u by del x is 0, so del v by del y is 0. That means v is not a function of y. V at the lower plate is 0, v at the upper plate is 0, and v is not a function of y, so that means v must be 0 everywhere. So after dropping all these terms, we recover the same equations as we had in the last slide. D square u by dy square is equal to p prime by mu. Same equations as in the last slide. This equation is to be solved with the boundary conditions u is equal to 0 and y is equal to minus b. That is, the lower plate is stationary, and because of no slip, the velocity of the fluid at that plate is 0, and u is equal to v naught and y is equal to plus b. The upper plate is moving with the velocity v naught, and because of no slip, the velocity of fluid near the upper plate must be equal to the velocity of the plate v naught. If we use this boundary condition to solve this simple linear equations, we get this solution. This solution has two parts. One, that does not depend upon the pressure gradient, and the other that depends on the pressure gradient. The first part is a linear velocity profile because of the motion of the upper plate that we have discussed earlier. The velocity varies from 0 at the bottom plate linearly to the velocity v naught at the upper plate. The second part is the velocity profile between two parallel plates because of a pressure gradient P prime. To obtain this flow, P prime should be negative. So minus P prime would give you a positive velocity. This, you can see, is a parabolic velocity profile with a maxima at the middle. The velocity profile here is the combination of the two, depending upon the various values of P prime and V naught. We can have different profiles. This parameter here, which we denote as a script P, determines the relative importance of the linear profile and the parabolic profile. The profile with a linear flow is called the Couette profile, and the parabolic profile is known as the Poiseuille profile because of the pressure gradient. For different values of P, script P, we can plot the various curves. The straight line curve in the middle is for script P is equal to 0. Linear. The velocity u by v naught varying from 0 to 1. For the value of this parameter script P negative, that means pressure decreasing in the downward direction. For the value minus 0.25, we get this profile, and for minus 2, we get this profile. Skewed parabolic profiles. For positive value P prime, that is for P prime for the pressure increasing in the downward direction, the profiles are shown on the left. This is for P is equal to 0.25. This is significant because at this value of the pressure gradient parameter, the slope of the velocity profile at the lower plate is 0. That means at this pressure gradient, the lower plate does not experience any shear stress. If the velocity gradient is 0, that means the shear stress is 0. So there is no shear stress on the lower plate. For P greater than 0.25, we have a region of negative velocity. That means the pressure drives the flow towards the left in the lower part of the channel, while in the upper part, because of the motion of the upper plate, the flow is in the positive y direction. The volume flow rate through this channel is determined by integrating u dy over y between minus b and plus b. Carrying out the integrated operation, we get q dot prime, that is the volume flow rate per unit depth, as bv naught minus twice p prime b cube by 3 mu. If there was no pressure gradient, then the volume flow rate would be v naught, and if the upper plate was not moving, the volume flow rate would be minus twice p prime b cube by 3 mu. Obviously, this kind of expression raises the possibility that there exists a value of v naught and p prime such that there is no net flow across the channel. These can be equated to 0, and then we can determine the value of p prime as 3 mu by twice b square v naught, for which the net volume flow rate would be 0. A positive pressure gradient pushing the flow backwards, and this gives you the pressure parameter defined earlier as script p to be 0.75. We draw the profile. This is what we have. The flow to the right is exactly equal to the flow to the left. The shear stress variation along any section can be calculated by tau is equal to mu du by dy, and that is obtained for the profile that we obtained as mu v naught by twice b minus p prime y. Note that the shear stress is constant across any section for the Couette problem. That is, no pressure gradient, but only the upper plate moving with the velocity v naught. Then we have constant shear stress is equal to mu times v naught by twice b. But the shear stress due to pressure gradient varies linearly. It is minus p prime b at the top and bottom surface and 0 in the middle. Of course, shear stress should be 0 at the middle because the parabolic velocity profile is symmetric. So dv by dy is 0 at the middle. Thank you.